And I just have some simple diagrams of how this could be done for some simple words, in this case like strings here. And just show that you have a certain number of what I call these entropes that are based on place, manner, and voicing. Sometimes voicing is not distinctive, and therefore it doesn't have an entrope by itself. And this just shows that for two different instances of the same word, like and, where it can be like, I said ham and egg, so every phone segment is pronounced canonically, because the person was really upset at the waiter trying to bring just ham and not ham and eggs. And in this case, the person could have said ham and eggs, where the and is reduced to just a syllabic nasal. And so the amount of information conveyed in the pronunciation of the word is extremely important for interpreting how that word is supposed to be decoded. Okay, so the lower the intrinsic information associated with the word, the more highly variable is the pronunciation over a broad range. So the corollary of that is, if you know where the information is, you can actually predict what the pronunciation variability is likely to be. And it's not just on the function words, which are true. It's true that they tend to be shorter, they tend to be variably pronounced, but it can be on any syllable, any word, depending upon the information content, which is why it's so important to have some sort of signal processing that detects that, like the stress accent labeling that I mentioned earlier. And so in the final part of my presentation, just want to talk a little bit about entropy-based pronunciation variation, that the amount of variability is likely to be correlated with the intrinsic information, and therefore you can estimate the amount of information associated with it, etc. And I show that here where you have different tiers. You have place of articulation, you have vowel height, you have voicing, all with certain structure. Notice that the voicing is contiguous within the syllable, for example, and you can actually use voicing as an implicit syllable segmentation. The energy contour also is highly structured. You go from low to high and back to low. You never violate that within the syllable. So there's huge amounts of structure and interdependencies within and across syllables that currently are not being taken advantage of in speech recognition systems, and I think would help a lot. And so this is just a very coarse flow diagram of all the different types of things you need to do, in my view, to actually be able to extract the information and the phonetic valence very accurately. I'm not going to go into any of this. You can just peruse it at your leisure. And what you can do then is to essentially build lexical models that are based upon discriminated phonetic features for each word in your training corpus, and have what I call an ensemble representation, as well as embed all the phonetic variation that you want statistically. But the important thing is that you then have to tune the lexicon to the pronunciation features. And this gets back to the point that Fred made earlier. I mean, this stems from the experiment that McAllister and Gillick did about 7 years ago, where they showed that if you could, in fact, tune the lexicon, the lexical representations exactly to the phonetic input, you, in fact, have solved speech recognition, at least for switchboard. But the key then is that the phonetic classifiers then ultimately have to be in the same form as the pronunciation models, exactly, to be discriminated. That's a very hard task, but I suggest that if you can do that, then you have largely solved speech recognition. And I think this is a task that's worthy for the next 10 years of our lives. So I just wanted to thank you for your time, and I also wanted, since I am the final speaker, I wanted to thank my colleagues in the Landmark group, because they've done a huge amount of work, much more than I have. And I wanted to particularly thank Mark Hasegawa-Johnson, who's put in a huge amount of effort into organizing, coordinating massive amounts of data preparation and meetings. And there's a lot of background work that you're not aware of from these presentations, and that Mark and a few other people here have been working for months to do. So I wanted to thank him personally for making this possible. Thank you very much.
So we even though we are almost 25 minutes over time, we'll give it another 10 if anybody wants to have a discussion or say something. Yes.
So one experience that we have for the switchboard test that is that most of the errors coming from functional words like the or those kind of words, they are with the least kind of the language model linguistic information and the least kind of acoustic information. And those kind of words are most likely without accents. And so
Exactly right.
does it mean
exactly
that
right.
we need to change the evaluation matrix to represent our research efforts, or?
Well, what you're saying is absolutely correct. So there seems to be a paradox on the surface, which is not really a paradox at all, which is that the words that provide the greatest problem to the speech recognition systems are often those that are most predictable and carry the least information. And yet they're scored incorrectly. In other words, the words are all scored equally, even though some are more important than others. And I know that people have been proposing for years to have something like a more concept-based recognition system. In terms of what I've spoken about, I think that it's not an accident that the recognition systems have this problems with these words, because these are the words that the human speaker thinks are the most dispensable, expendable. You don't really need to decode them that well to understand the gist. The only difference is that the human has huge amounts of knowledge and context that the machine doesn't have to fill in things that they don't accurately decode. A machine is much better at decoding isolated vowels and consonantal segments than the human is for that same small time window, because it's been trained. And what this really says is that for machine recognition to be as good as humans, you have to embed many other tiers of knowledge. I'm not sure that's really what you want to do here. I think you really want to provide reasonably accurate transcripts without having to worry about whether that was an or a da or an in, except in cases where it's very important. And usually the speaker takes care of that.
Excuse me, what is the Rosenfeld result from '95? Isn't it that there is no bias toward making errors, short word errors? Yeah. Isn't that how it was? So where do you get your information from?
Well,
I mean,
it's the
if
figure
you actually measure it,
two-thirds of the words are function
exactly.
words.
Most of the words are function words. Sometimes you're going to make an absolute term, but
That's right.
errors are going to be most of the function words.
Yeah, there are no.
oh well, then his remark is vacuous, right?
No,
I mean, the point. I mean, maybe I remember the Rosenfeld result wrongly, and
no, I think you remember it correctly. The fraction of function words you get wrong is roughly the same as the fraction of function words you get wrong. And the point is, do you really want to improve your recognition by improving accuracy on the function words? You probably don't.
it's a valid question. I mean, the one thing that does correlate with shortness, reduction, and lack of accent is the proportion of deletion errors is much greater for the unstressed syllables, which are mostly in the function words. But otherwise, your comment is very valid. In fact, there is otherwise no impact in terms of stress accent.
But
You can't agree with both assertions. I mean,
No, it really depends. No, it depends what your object is. If your object is perfect word transcription, where you're really assessed, as all these sites are, on exactly how many words you get right, then you have to be concerned about the function words, because they count for 2/3 of all the words.
even if they didn't count, you want to still recognize them, because through the language model,
The language
provide
model,
extra
yeah.
That's right. It's
emphasis
a very valid point.
to the other ones.
And it really matters for structured language models.
Yeah.
Not for certain function words, like the word like. It has no syntactic information or semantic information.
In that case, it might be
That's
a
peculiar.
switch
believe
word
it.
I
for
want to point out that this is a discussion of the whole group, not of the last talk. Did you have something to say, Jack?
No, I just think that there's an awful lot of thought gone into this over the last 20 years, and generally will come to the conclusion that without picking certain winner applications, it's very difficult to drive the technology across the board with anything less specific than word error rate. All the cheats have been done already. All the easy wins of multi-words and so forth have been done. So really, to try to cancel out some effects such as the presence of function words, it's really not worth it if you want the whole technology to progress. If you want a particular application, then by all means, optimize for whatever that application calls for, like names or addresses or something of that sort. But if you're going to drive the technology at a higher level, people have really tried very hard to come up with something better than word error rate, and it just hasn't, nobody has.
So I have a problem, I have a question about the landmark approach. I would think that one of the problems is that if you want to detect the various landmarks, then everything has an error rate, and so you're then accumulating an error upon error upon error. And so the accuracy with which you would have to do the detection is maybe staggering, and we're not capable of it. So that's number one. Number two is a possibility that the model that Karen, I think it's Karen who showed the network.
Karen.
Pardon?
Karen. Yes.
Karen. All right. The model is, very arbitrary. It's very complex, very arbitrary. And do you believe that that's where the problem is? That if we only had a better and more model, then you could sort of knit together the various landmark detectors.
Can I give? So I'll give my answers and then open the floor because others may have some. As far as the compounding of errors goes, the approach that I've been advocating and that we've actually started to implement with our most recent system is to have a redundant set of distinctive features that acts essentially as an error correcting code. So we have, in addition to classify a three-way place of articulation distinction, for example, we currently have 3 different binary classifiers, and one could imagine constructing an even more intelligently based design system that basically says that up to a certain number of classifiers incorrect, we can correct those mistakes by looking at the outputs of all of the classifiers together, which is what the systems that Karen and Katrin have designed to do. They look at the outputs of all classifiers together. On the second question, sure. When you factor phonemes into several dozen different factors, there's the risk of it becoming arbitrary. And the approach that we've taken to avoid arbitrariness this summer is to design it based on linguistic theories of pronunciation variability, based on studies that try to explain long lists of examples of pronunciation variants that can occur in spontaneous speech in the most concise way possible.
I also have 2 answers to that question, if you don't mind. So I guess when you're actually so you said that you're compounding the errors by doing an initial classification, say based on SVMs or based on neural networks or whatever it is that you're doing. But when you're actually doing encoding, you're actually not making hard decisions at the phone level. It's actually probability distributions which are being given to a higher level. So you're actually not abandoning the uncertainty. You're still actually representing the fact that there is uncertainty by there being probabilities. And by doing that, you're actually able to essentially bypass errors in the same sense as a Gaussian can do. You would never, for example, use a Gaussian mixture and say it's either 1 or 0 based on whether or not the feature vector is equal to the mean. It just wouldn't work. You use the Gaussian to give you a sort of a degree of uncertainty about whether or not the HMM state corresponds to that Gaussian. And then the second question is, I think it's much less arbitrary than the HMM.
Well, maybe it's much less arbitrary, but it's much less elegant.
No.
I don't think so.
It's linguistically more elegant. It's mathematically more complicated, so maybe
Right.
mathematically it's less elegant, but linguistically it's more elegant.
Yeah, but that's what I'm referring to. No, because linguistics is in the eye of the beholder, but mathematics, that exists.
Well, linguistics is empirical in some sense. A linguistic theory either works on data or it doesn't.
Well, the fact is that when we started doing translation at IBM, we were hoping that we would get around the left-to-right way of decoding things, and that we would find IELTS of reliability, and that surely table is translated in French into double, and we could bet on it, and we would have these islands of reliability and somehow connect it together, and it failed. And so we still went from left to right. And okay.
Whether you go from left to right left doesn't matter.
No, of course not. Left to right to left. The question is whether you can skip it out.
You're computing a score. You're computing a probability score of a probabilistic model over a temporal sequence, and you could go inward and outward. You could go a little bit here and a little bit there and a little bit here.
Yeah, but you don't know how to connect it because you don't know how many words are missing in between. When you say that I know this word and I know this word, you don't know how many there are in between, and that's the problem. Anyway, okay.
So I have a question about the landmark approach, which I think is...
The what approach?
The landmark approach, as implemented this summer. So as Jeff says, you're still using probabilities at every step, but they are probabilities over discrete things. So you say either this feature exists or it doesn't, or the mouth is in one of, the lips, for example, are in one of three positions. And I wonder whether you might get some benefit by taking densities over a continuous variable instead. The reason I'm wondering this is if I'm a conductor and I say, body off, then there are actually two vowels in there at the beginning. I mean, I can hear it, or I can feel it in my mouth or something, that the everybody is something like e, a, e, or e, ba, e, except there's very little dynamic range between the vowels. But I wonder if there's information there that might be usable. So there's some trace variation.
It's a good. I'm not sure if I have a good answer for that. A continuous, so basically replacing a discrete articulatory phonology with a continuous articulatory phonology, or it just
yeah, that's
that? I'm sorry?
Yes, that's right.
Yeah. It's an interesting idea. I'd have to think through the theoretical implications. One point to consider is that I don't think there's any computationally feasible way of doing that right now.
There is. Actually, Larry Saul has a model called Markov processes on curves that he worked on a couple of years ago, which I think would be quite appropriate for this.
Okay.
So,
I mean, there's continuous stuff elsewhere also. So, Steve, you could say a lot of things about secondary stress versus primary stress, right?
In our transcribers, we're not able to reliably mark secondary stress. We tried that originally. And so what we have them do is to say definitely heavily stressed, definitely unstressed, and then everything else in between goes in that intermediate category. They could not reliably do it. And our interlabeler concordance is consistent with that. It's very high for the extremes, the high and the low, and quite mixed for the intermediate. So I'm not convinced that there really is this formal secondary stress.
Well, but that might actually argue for it being an underlying hidden continuous parameter.
Right. Well, actually, that's exactly what we ultimately concluded, that there are, in fact, two classes of stress in English, accented and unaccented. The unaccented is not graded, but the accented is graded, and that's actually how it seems to work. And so our ultimate system has 5 levels in the automatic system, where we averaged the 2 transcribers to do 45 minutes. We've done 3 levels. Where they disagreed, it was usually in just half a step. And so we then took the averages, and so it's actually a 5-level system. And I talked to Gunnar Fahn about this because he had done a system in Swedish where they had 30 different levels of stress. And so I sort of asked, are you sure that you can distinguish that? And he said, well, actually, they were only consistent sort of within about 5 levels. So it's actually about the same 5-level granularity as we have for English.
My experience with this is looking at F0 data, and if you want to build a predictive model of F0 contour, given lexical stresses and tone positions in the sentence, then the predictive model looks like there's continuous variation.
That's exactly right.
So I think the single biggest problem with this is the need for this closely transcribed phonetic data transferred to the phone level. I mean, even with the simplifications that you made, I think it just doesn't scale, and because you have to be able to train. Basically, all you really know exists. Okay, is the waveform and the words, and the words are already sort of iffy in places. But that's sort of what you really can rely on, and we all know the phones they don't really exist, right? But they happen to be a useful way for you to tie certain parameters in your Gaussian models, okay? And because that's all they do, and everything else is figured out by the HMMs, that's why HMMs work as well as they do. So if you can cast this idea of landmark modeling in a similar framework, where you let all the details be figured out by the data, then I think it can be made to work. But until you figure that out, you rely on having these discrete decisions about landmarks being here or there, it just won't fly. So.
Can I comment on that?
Yeah.
So it sounds like you're arguing against hidden variables. And I think,
No.
what you can do, and you know this, I'm not surprised. Right. So I mean, what you can do is essentially do embedded retraining. So you've got the acoustics and the words, but you also have phonology and phonetic rules and linguistic knowledge.
That's a perfectly fine.
So what you can do is essentially specify partial orders over these times.
Exactly, that's what I'm after.
And then do an embedded training one where the partial order gives you zeros or something, and then the something is done by EM in an embedded training.
Well, that's exactly what I was.
That's what you're arguing.
Yeah.
Okay. But it's kind of like you said, until you can figure it out.
Well, he hasn't figured it out.
Well,
just as a direction.
Nobody has figured it out.
Yeah.
But that's Morgan does that. I mean,
so what are Morgan's results since he's figured it out?
well, I think it gets
He's not
better
doing,
when
he's not
you use
using landmarks, he's using phones.
No, he's using phones, but he does the embedded like kind of stuff when you have embedded.
Yeah, but that's just doing realigning everything on every iteration. That's not different from doing phones.
No, but it's the same idea. But I think it's just
Okay, Bill.
Well, I was just wanted to follow up on something that Steve said. I was sort of dismayed to see him reject the sausage, the confidence set approach to things. Because, I mean, I have this idea that a priori, linguistics is useless.
Is what?
Useless. But the great thing about the sausages is it turns an a priori problem into an a posteriori problem. So instead of trying to solve the entire world, I as an engineer can go to my friendly linguist and say, just solve these 3 words. And it carves the whole huge world up into a very small number of problems, well, actually a very large number of small problems. But you can actually say whether or not your intuition, which is, very compelling, but we don't know what problems it's going to solve. And the beauty of this other approach is it actually defines the problems in there on this sort of scale that people seem to want to work on. So I was sort of dismayed that you don't like the idea.
Well, I think that there may have been a miscommunication. I actually think that what Country did was extremely clever. I think the problem is what she ran up against in terms of the amount of data that would be required to sort of make a significant impact here. And so yes, if you had huge amounts of data, it probably would have done a lot better. But I think you're always going to confront this data bottleneck. I think that this is something that people have been trying to postpone for years, saying, well, we just need more data. But ultimately, this is not the way to solve the problems. And so you have to figure out some way of doing this with minimal amounts of data. And if you can do it with sausages, that's fine. But you still have that problem. And you will for eternity. And you just have to deal with that. That's the only point I really tried to make there, not against the sausages.
Well, it's 5:15. Thank you for coming, and see you tomorrow.